Now let's understand what are the elements of the queuing system, right? The very first element of the queuing system is input or arrival distribution. So what is going to happen is that the customers or the vehicles or the machines are going to come to get to at the service facility. So generally what will happen, they will follow some pattern, right? So what is your input and input or arrival distribution? It is nothing but it is representing a pattern in which the number of customers arrive at the service facility, right? So it is also represented by the inter-arrival time, which is the period between the two successive arrivals. So generally, to just to remember, it is representing a pattern in which the number of customers are arriving at a service facility. So if I say that every customer is arriving after 2 minutes, so what is that 2 minute? 2 minute is nothing but that particular, it is giving the information about the arrival distribution. So after every, I can say that every customer, there are, like I can say there are 60 customers arriving in 1 minute. So what is this? This is the arrival distribution, right? It is representing a pattern that after every second there will be one customer or one vehicle or one machine that will be coming to that particular service facility, right? So there can be particularly the now it may so happen that no, normally if I sit at a shop and I am measuring the time between two successive arrivals, I can I can tell that those time can be equal or unequal, right? So those time can be like the first two customers are, each of the first two customers have arrived after 1 minute, and after that every customer has arrived after 3 minutes. So it can be an equal what you can say equal arrival time pattern, or there can be an unequal interval pattern or arrival pattern in that. But if their probabilities are known, so if you know what are their probabilities, so we can call it as the random arrivals. If the probability, the arrivals can be random, the arrivals can be equal or unequal. But if we know what is the probability of each of this each of these arrivals, so we tend to call it as the random arrivals, right? Now nextly, the number of customers arriving per unit time is called as the arrival rate, what I have already told you. And in most of the example of business world, the rate is random, that is no logical pattern is observed. So you will be agreeing with me on this particular point that the if any business is taken, I can't predict which customer, no, I can't predict how the customers are going to come. I can't predict what will be the pattern in which the customer will be going to come at my service station. So here they have said that the rate is random. Random matlab kya? What is the meaning of random? It can be unequal or unequal interval, but their probability is known, and that is no logical pattern is observed, right? So the pattern of customers arriving at that service station will be different. So when arrivals are random, we have to know the probability distribution, right? And probability distribution describing the arrival time specifically between the time between the arrivals. And particularly there are many management studies that have taken place, and all these management researchers have now they are saying that the arrival pattern can be best described as Poisson distribution, and it is represented by a value called as lambda, right? So now what is a Poisson distribution, that also I'm going to see. It is not the part of your syllabus, but I'm only making you understand how this Poisson distribution is there, how the Poisson distribution is represented graphically, and that will be helping you to understand or imagine what is the arrival pattern that I'm talking about. Now, what is the Poisson distribution? It is the discrete probability distribution of the number of events occurring in a given time period, given the average number of times the event occurs over that particular time or that period of time. So suppose I'm for 24 for a 24 hour I'm sitting at a McDonald's, and I am recording the time interval between every arrival, right? So I'm noting that this particular customer A has come after 1 minute, customer B has come after customer A, and the time interval is 3 minutes. And all this such type of customers are noting that what is the successive distribution, successive what you can say, successive arrival time between all the customers that have come in 24 hours at that particular McDonald's service station. So after that, what I can predict is that I can represent it in this that particularly probability graph. So if I find out for 1 minute service distribution or 1 minute arrival distribution, how many customers are arriving? Like for after there are 10 customers which are arriving after 1 minute. So all the 24 hours data, if I find out what is the successive duration of how many customers are arriving after 1 minute. So from all this 24 hours data, I can get like 10 or 15 customers which are arriving, and I can find out the probability of arriving customers in 1 minute. Similarly, I can go for 2 minutes, 3 minutes, 4 minutes, and I can draw a graph. Now on this graph, you can see here it is X, which denotes the interval of it denotes the time interval for which the customers are arriving, and this is the probability where I've no, this is the on y-axis here. Here you have the probability mass, or here it is nothing but the probabilities that I have represented. Right now, if I start to plot the graph, like after one, what is the probability for for the customers to arrive after 1 minute? What is the probability? So I'll be drawing a graph, and now here I've represented it like here it is 10 minutes, 20 minutes, 30 minutes, and 40 minutes. So I'll be getting a bell-shaped curve, right? And this is nothing but the Poisson distribution. So I've denoted what it is, just the probability versus the arrival distribution graph. I've just plotted it, and you'll be seeing that this particularly is showing a bell curve, and the maximum value where obtained is nothing but the average value for it is nothing but the average value for the time for which the probability is the maximum. So this particular value is nothing but your lambda is equal to 25, right? So it is between 20 and 30. So I said that it is lambda is equal to 25. So I can say that the arrival pattern for that particular McDonald's is 25. That is 25 customers. Where it is I can say that it is the arrival time, the average arrival distribution is of 25 minutes, right? So this is how this particular thing has been can be represented. You do not have to there is no particularly it carries no weightage in your examination, this particular distribution. Just to get a sense, you'll be getting a bell curve, and the maximum value of it is nothing but the lambda is equal to 25, so which is also called as the arrival distribution here, right? So all this is nothing but your particularly the arrival distribution, and it is best represented by the Poisson distribution, right? Now here for the arrival distribution, we have understood that the particular there will be equal and unequal intervals, but their probabilities should be known so that they can be called as the random interval, and if they can be called as the random arrival. And if the information about the random arrivals is plotted against the probability, you'll be getting the Poisson distribution, which is best explaining the arrival distribution. The mean value of the arrival rate is represented by the lambda here, right? So let's move ahead and understand. Now we have seen the arrival distribution. After the customer will get service, so there can be a service distribution as well, and it is also called as the departure, the departure of a customer after getting the service. So now what is this service distribution? Represents a pattern in which the number of customers leave the service facility. So previously we have seen the pattern in which the number of customers are arriving at that facility, and here in the service distribution we are going to see the number of customers leaving the service facility. Now it can also be represented by the inter-departure time. Previously it was inter-arrival time. Here it is inter-departure time, or is also called as the service time. So which is between the two successive services. For arrival distribution, it was between two successive arrivals. In many cases where service time is random, it is best described by the exponential probability distribution. Now your arrival distribution was best represented by the it was best represented with the help of the Poisson distribution. But here it can be here with the management researchers and the management studies have proven that the uh, distribution, the departure distribution, is best explained by the exponential probability distribution. Now, this particularly the rate at which one service channel can perform the service, that is number of customers served per unit time, is nothing but your service distribution, or it is called as the service rate as well. And the service rate, the mean value of the service rate, is represented by mu. Previously for the arrival distribution it was lambda, here it is mu. Just to give you the understanding about the exponential, the shape that will happen for a exponential distribution. So this is the shape that you'll be getting if you are drawing an exponential probability distribution. So again, on the x-axis, that will be the service time. On here it will be the probability. So you will be seeing how the exponential service distribution is happening here. Again, here only you have to remember very importantly that for your arrival time it will be the best representation can be done by the Poisson distribution, and for departure, that is for your service, the best representation can be done with the help of the exponential service exponential probability distribution. And you can remember the shapes of both of this graphs. In case of arrival distribution, it was a bell shaped. Here you can see it as an exponential line, as the distribution in itself is the exponential distribution. Right now, the next element that we are going to see regarding the your queuing problem is the service channel. Right, so service channel, now it is what particularly previously said. Also in our graphical representation, we have seen that the system can have a single or a multiple service channel. A single channel, what particularly for a single channel, there will be only one service facility, and the persons will be waiting for that particular service station to provide a service, and they will be standing in a queue. For this can be a best for a single service channel, the best example can be of the can be of a doctor, a clinic, a clinic which is located in your town, in which there will be only one doctor and the patients are waiting in a queue to get attended. Right, so if you go at a if you go at a bigger hospital, there can be many doctors, and then particularly you can say that it is a multiple service channel. So depending upon what is the type of disease that person has, the person is sent to the different doctors for getting checked up. So that can be a multiple service channel. But for normal for the normal clinics that we have, there is only a one single specialized doctor that is sitting, and the persons are coming to get addressed or get treated by him. So these are the best example of your single or a multiple service channel. So now for multiple channel, there again you can particularly see for a multiple channel there can be a parallel series or the complex combination of the parallel and the series combination. Okay, so for example, if I have to think of a parallel service, best example is of a barber. Right, if you go to a saloon, there are like 4 to 5 chairs, there are 4 to 5 barbers that are particularly attending the customer, and at a particular time there are like 4 to 5 customers that are getting attended by that different barbers. Right, so that is a parallel service channel what we have. Right, it is a multiple service channel. Remember, it is a multiple service channel because there are like 5 chairs and 5 barbers, but all of them are attended at the same time, and hence it is called as the parallel multiple channel. Right, now again the multiple channel can be in the series type as well. So what is a series type? So for the best example is that if you go out to take a you had experience the admission procedure at our college. There are various desks. At the first desk, you will be handed the admission form. At the next desk, they will be checking you your Xerox copies of the documents that you have attached. At the next counter, they will be checking the original documents along with the Xerox copy. After that, there will be the procedure for paying the fees. After paying the fees, you will be passed towards an ERP entry. After ERP entry, you'll be coming to the uniform section, and after that, after this all this activities get completed, then your admission then your admission process ends. So at this particular, the prime objective is to get an admission, but to have an admission, you are visiting various desks, right? So that is what that is called as the multiple service channel, but which is acting in the series, right? So this is the best no this is the best example for your multiple channel. Even no the now this is I've given you the example of an admission. Even if you go for casting the vote, right? In the case of your Lok Sabha, Rajya Sabha election, the very first is the very first thing that you experience is your this at the store itself you are being fixed. That means they're telling you to keep your mobile outside and no talking, and you have to maintain the silence. And then afterwards, when you go inside, so you will be seeing that there are a number of persons that are standing in queue as well, right? So when you enter that particular, after being frisked, if you enter, they will be checking your original Aadhaar card or an election card, and then they will be telling you to write your name. Then they will be giving you a slip, and after getting a slip, then you get to cast the vote, and again you have to submit that particular slip. So this particular is what you are going to cast a vote, but you have to visit a various desks. Then only your casting of the vote gets completed. Any one desk if you miss, that particular your objective is not going to get fulfilled for the both examples. So for even for your admission, if you're missing any desk, they will be sending you again to that particular desk and tell you to complete that particular process, and then there will be next process can be done. So these are the examples of your multiple channels, right? And multiple channel can be a parallel, it can be a series, or it can be the complex combination of parallel and series, in which the processes of like parallel activities and the series activity are getting repeated. So that can be a complex process. You may think of an example of it, right? There can be particularly one server model going ahead for a queuing model. So it is if there is only one server, it is called as a one server model. So you have only one server, and it can be a multi-server model. So there are a number of parallel channels each with one server. So that is your multi-server model, right? So let's move towards our next element, and that is your service discipline. Now what is a service discipline? It is the rule it is the rule by which the customers are selected for the from the queue for the service, right? So what is a service discipline? It is the rule by which the customers are selected from the queue for service. Now the normal what we can say, the normal rule that we follow for selection of the customer is first come first serve, right? Everyone will be agreeing with me regarding this particular rule. It is called as the first come first serve rule, right? So particularly, let's talk about this first come first serve rule. It is very, very common, and it is being denoted by FCFS. So that is the person who has come first will be getting addressed first, he'll be getting served first, and the next person who have come after that will be getting attended, and the process will follow, right? So the normally we follow, everywhere we follow this first come first served. You have at your ATM machines for taking the admission, when you visit a hospital, everywhere it is evident that the first come first serve policy has been particularly followed. Now there can be the last come first serve policy. Now it is you can think that it is an hilarious, right? So last come first serve, and that is not possible. But can you think of an example of last come first serve policy? Anyone? You can write it in the chat box. I'm stopping the sharing. If you can tell me, no, how come last come first served policy is followed? Yeah, anyone, no? Last come first served policy. Any example that you can give regarding the last come first served policy? Any typical example that you have you have seen around you, which anyone? Okay, chalo. Let me give you one example regarding the same, and then we can move ahead. Okay, so last come first policy for last come first serve is normally no, it is normally seen in the case of the go downs, right? So if you see a go down is filled from the it is filled from the extreme end and towards it towards the entry of that particular go down, right? So what will happen is that the first if a truck comes, the material that is stacked in the truck will be getting emptied in the go down, and the first material that will be coming particularly, it will be stacked at the bottom, and the new material, the last material that has come from the stack is particularly will be at the top. So if you see a go down, the last bag that has come into the go down will be served first. So that is what it is, LCFS. So that is your last come first serve policy. So this is the actual example of your last come first serve policy. And no, particularly even if you're visiting any temple or so, and if there is any VIP that is coming, right? So what will happen is that you'll be made to wait at that particular location till that VIP comes. He is taking his darshan at the temple, and then he is leaving from that particular location. So what is that particular VIP? Now this is this is an example that we normally practice. So if there is any politician or a person of the VIP nature comes, so that particularly the other normal people will be kept aside. The person who is the VIP has come last, then too will be getting served first. So that is also the example of your LCFL, that is the last come first serve policy. Now there can be the service in random order, SIRO. So I don't know, there is no practical example of this, but no, particularly service in a random order can happen. So I can particularly, if the customers are coming, so particularly depending upon I can't give a practical example of this, but even in the thing, if I have to closely relate an example towards this particular sequence, so that can be with respect to when you go to a hotel and you have to take away your order, and there are like 2-3 persons who have come at that particular hotel to take away the parcel. So the person, it may so happen that the person who has come after you is getting so he is getting his parcel first, because he has ordered something which was ready, or particularly which took less time for getting ready. So that may happen, that a service in random, or depending upon what you are what you have ordered, depending upon that you are getting the service. So if I've ordered like the lunch of 10 people, so I may get my order a bit late, and a person who is coming is to take only some like 2 chapatis from that particular hotel, and he may get served first. So that can happen, and that is nothing but service in random order, depending upon the psychology or the philosophy of that particular service station. Again, priority is one of the service discipline that you can follow, that normally we say. Even this particularly holds good for your particularly your VIP example is also particularly uh, best suited here. Or particularly if I'm at a airport, and if at airport I'm standing in a queue, and a person who is having no they who is having, I don't remember what is the no or so a person, I have a economic class ticket, and a person who is having a business class ticket, so particularly they will be giving the priority for a check-in to a person who is having a business class, right? So that is the business class particularly depicts the priority. So that person will go to the he will be directly taken to the first of to the head of the queue. But at that particular no that is called as the priority. And there can be an preemptive priority as well. So what is a preemptive priority? So that particular person who is having a preemptive priority goes to the head of the queue, but he also displaces any unit which is already being served. In priority, that is not the case, right? In priority, the person on the counter will get first served, and then the priority person will be getting addressed. But in preemptive priority, if someone is on the service facility, even that particular the service of that particular person will be stopped, and you'll be the person with the priority will be given the no he will be given the priority. So that is the example of the preemptive priority. So this is nothing but your service discipline, which is also one of the element that we consider in the queuing model. Now, what is affects? So your service discipline will affect the time for which an individual has to wait, right? So if I've no if I'm not a non-priority person, so what will happen? Ultimately, I will be getting the service, right? After some time, I'll be getting the service. But what will happen is that the time for which I have to wait in a line will increase because of that. Okay, so I'll be getting the ticket for the aeroplane. I'll be board. मेरा भी check in होगा. मैं भी मेरे destination पे पहुंचने वाला हूँ. But क्या होगा? जो मेरा टाइम मेरा क्यू में जा रहा है, what will happen? That time will increase. So your service discipline, it affects the time for which an individual has to wait in a queue, right? Now the next element that we have is the maximum number of customers allowed in the system, right? So how many? So particularly it is the it is also termed as the capacity of the system, and as the name suggests, it is the max number of customers number of customers that are allowed in the system, and that number can be finite or infinite as well, right? So it can be a finite or infinite. So only a limited number of customers are allowed in the system, and a new arrival customers are not allowed to join the system unless the number becomes less than the limiting value. So if I'm having a finite, if I'm having something, if I'm having a finite number to be allowed in the system, so this particular rule is being followed, right? So only limited number of customers are allowed in the system, and new arriving customers are not allowed to join the system unless the number become less than the limiting value. So now particularly with I can give you an example for this particular type. Now because of the lockdown, what has happened, there are entry restrictions at many of the places, right? Now for example, I purchased my grocery from DMart, right? And till few days back, till few days back when the lockdown was very serious, what they used to do is they used to allow only 20 customers in a particular DMart. So after one of the customer would come outside of the DMart, the another person will be given an entry. The another person will be given entry into the DMart. So what is that? I can say that the capacity of the system is only, it is a finite, and the value is 20. So it can't be 21, right? So if there is a 21 number of customers that are inside that, they will be penalized, or that particularly is not accepted. That is not accepted by the system, or the by the person who has decided that particular system, or who is the head of that particular system, right? So 20 is the number that they have decided. Only 20 number will be at the time, only 20 people will be inside that DMart, and one comes, if it happens to be 19 inside the DMart, they will be sending one more person and it will be 20, right? So this is what this is now particularly as a finite system. And the same example can be taken for an infinite system. If you now it is an unlock, right? It is not a lockdown. And now if I visit now when I visit this DMart, they are not checking how many customers are inside. They are purely sending all of the customers that are coming in to inside the DMart. So now what has happened? The capacity of the system now has become from finite to, it has changed to infinite. So when it was normal before lockdown, it was infinite only, right? But during the lockdown, we made that particular system finite, and now again some of the relaxation has happened, and then the system is now again infinite. So I think you are getting what is the particularly the what I'm trying to tell with the help of this capacity of the system, right? Now let's move towards our another element, which is called as the calling source or population. Now the arrival pattern of the customers depend upon the source which generates them, right? Few potential customers, if there are only few potential customers, then the the calling source can be, or the population can be said as the finite. And if there are like large number of potential customers, then that particular thing is said to be an infinite. Okay. So now let's take an example for this particular thing. Now, if I'm there are a particular here you can assume a 5-star hotel which is serving you a vada pav, and you can particularly again take a roadside vendor who is preparing vada pav and selling it on the at the food at particularly on the curb of that particular road, right? So what will happen is that at both of the end, what will happen, the commodity that you are going to get or purchase is the vada pav only. But what will happen for if I'm thinking of going to Taj Mahal, so I should have at least like 200, or I should at least have a capacity to spend 300-400 rupees on one single vada pav at your Taj Mahal, right? And particularly if I'm intending to buy that vada pav on the road, I can spend like 10 rupees only. So the people that are willing to spend 10 rupees on the vada pav are infinite. So your population for that particular vada pav at this particular condition goes to be infinite. But the people who are willing to eat vada pav inside a 5-star hotel by spending like 400 rupees on one single vada pav is what it is only finite. So you have very few potential customers that are willing to get inside a 5-star hotel and eat a vada pav of 400 rupees. So what is your population happens to be a finite, but there can be infinite people who are going to invest, or who are willing to give 10 rupees and eat a vada pav. So that population becomes infinite. So same can be the case in which you have to buy a 4-wheeler Rolls Royce, right? So Rolls Royce, the capacity of people buying a Rolls Royce will be very few, or the families who can afford the Rolls Royce is very few, and the potential customers can be finite for that particular thing. Okay, but for some another thing, for example, nano, right? So for nano, which costs to around like 1.25 lakhs, there can be infinite potential customers, right? And that particular is the population in this particular case. So population also particularly decides the arrival pattern, right? So if you see at a 5-star hotel, the person who will be coming to eat vada pav, the customers that will be coming to eat vada pav will be, the arrival pattern will be different. It will be like after 2 hours, one customer is coming to eat the vada pav, let's say that. And the arrival pattern will be different. Here every second one of the person can come and ask for a vada pav, right? So this is how the population will particularly change your arrival pattern. Let's move ahead and address this particular last point of today's lecture. So what can happen is that I can think of a customer behavior. Last element is now your customer behavior, and customer behavior also influences the it also influences the queuing model. So now if customer decides to not enter the queue since it is too long, he is said to bulk, right? So the terminology that we normally use is the bulking. So if I'm passing, if I have to withdraw some money from the ATM, and if I see a very long queue at that particular location, so no, I won't be waiting. So what I'm doing in the language of the queuing model, I'm getting bulked, right? So another case, it can be if a customer enters the queue, but after some times he loses the patience and leaves it. So he is said to have it. He is said to have reached, right? So that is the normal terminology that particularly is being used. So if the customer now has entered the queue because of the necessity, and he is, but after sometimes he is losing the patience and he is leaving that particular queue, so he is said to have reached, right? So lastly, very important, when there are two or more parallel queues and the customers move from one queue to the other queue because of some reason, then is said to be jockeying, right? So jockeying, jockeying is the terminology that is being used. So there can be, you can see that the customer is behaving particularly of the sort of, he may be bulked, he may no, he may get bulked, he may get rinsed, or is performing the jockeying activity, or is changing the queue from